It is my pleasure to introduce Olena Karpel from AGH Krakow, who will talk about dynamics on the fast space for generalized Bratteli diagrams.
So thank you very much for the invitation. It's great to be here. Always love to.
Hey, you spent 3 years here.
Yes. And so I would like to talk about the joint work with David Borel, dierences, and Lisa, and it was generalizations of standard Bratteli diagrams. And so standard Bratteli diagrams turn out to be a very powerful tool to study, for instance, Cantor dynamics. And generalized Bratteli diagrams are models for Borel dynamical systems. So let us see what is a generalized Bratteli diagram. And let's use the abbreviation DD. So let's see what are the differences, what kind of problems we have. So we will study the dynamics of these diagrams, Vershik maps, their equivalence related invariant measures, and see what results we can generalize what we call standard diagrams and what is completely new. So a generalized Bratteli diagram is a graph which has a vertex set and an edge set. So the set of vertices is partitioned into countably subsets, which we call levels. And now, unlike standard Bratteli diagrams, all our levels will be countably infinite. So I mean, actually, this is very important. So we have, and here just it will be more convenient for us to start already from this zero, which has countably many vertices. So one can imagine that we have some similar vertex for people who are used to standard Bratteli diagrams. We can imagine that there is a single vertex and there are edges here. But we will not draw it. So we will start this with zero, and then we have the 1, and we will all count to the infinite. So we can enumerate them by natural numbers or by integers, for instance. Usually we will use natural numbers or integers. And we have edges. So here the edges come from E0 or E1. And as for standard diagrams, they are drawn only between consecutive levels of vertices. So again, the set of edges is partitioned into subsets. So here again, we will be different from standard diagrams. We will start with 0. So each edge is directed downwards. So it has a source and a range. So for the edges from EI, the sources belong to vertices vi, and the ranges belong to vi plus 1. And we have a rule that every vertex has an outgoing edge, and every vertex except for V0 has an incoming edge, the same as for usual Bratteli diagrams. So for every vertex, there exists an edge such that this vertex is the source of the edge, and for every vertex except for upper level, again there is an edge such that this vertex is the edge. And now we have another condition. We want that for every vertex, there are only finite remaining incoming edges. So now we have infinite levels, right? And there's a new condition which applies to the following. So maybe we'll have this is the first condition. This is the second condition. Maybe I can move one here. So for every vertex except for outer level, we consider all edges that end in this vertex. So all edges for which range is this V, and this is a finite set. Okay. Should we wait on the
Maybe wait.
Yes. So this is a group for us, we have this for every vertex, the set of edges which have the range in this vertex is fine. And then we have the generalized Bratteli. We consider the set of all infinite paths that start from upper level and go downwards. So it's one set of. So each path is a sequence of edges. The structure of the range of the previous edge is the source. And similarly to standard diagrams, we put here a topology generalized by Miller sets. So if we here a small detail. So we don't write here initial vertex. So we will consider at once that these points of greater 0 level are Miller sets. And then they are subdivided into similar subsets. So if we have a finite path, and with 0, so on the end. We will consider a cylinder set if the set of all infinite path which at the beginning pass through this finite path. And with this kind of topology, also it's this topology generate there is a metric which generates this topology. So we have two infinite paths x and y. It's also the same as the constellation diagrams. We say that the distance between x and y for two different paths is 1 over 2 to the power I, where I is the minimal natural number or 0, minimal non-negative integer, is different from uniqueness. So this is ultrametric. It's and with this metric, which generates this topology, our XB is a polar space. But it can be non-compact because we have countably many vertices. So XB is a completely separable metric space. It's a polar space. And we will consider only such diagrams for which XB is uncountable, and there will be for which there are no isolated points. And so we can consider here Borel sigma algebra, and then we can associate a standard Borel space to this polar space. So we have a Borel space, already the base space, with Borel sigma algebra is our standard Borel space. And so let us also notice that this graph is completely determined by the sequence of incidence matrices, which tell us how the edges are drawn between consecutive levels of vertices. So it's again the same as for standard diagrams, but our matrices will be enumerated like the indexed by countably infinite sets. So we have here VI and VI plus 1. In between are edges from VI, which are drawn corresponding to the rule given by incidence matrix Fi. So Fi consists of, let's denote like this, the edges of such matrix. So we look at this lower level VI plus 1, and W belongs to the upper level VI. And this element tells us the number of edges between V and W. So we can maybe also use notation in the W is the number of like this. So this will be the set of all edges between V and W, and this will be the number as cardinality of this set, the number of edges between we and now so our with value I is exactly this number of edges. And so this matrices M has since we have this property, in each row of the matrix M, there are only finitely many non-zero elements. Because we have only finitely many incoming edges, so we have here only finitely many vertices to which we can be connected. So in the row there will be only finitely many non-zero elements, and such matrices can be multiplied. And so we can use this telescoping for the Bratteli diagrams, and still we have a well-defined incidence matrix with finite elements. So let me okay, this one.
Is something special about choosing that finitely many vertices are going to vertex and not starting?
Yes, because if I have to start, this has local components. Ours here we our space and is not compact, it can be locally compact or not locally compact. So basically take a question so that necessary and sufficient condition for local compactness is that the vertex has finitely many outcoming edges, so that every cylinder set basically is a unit of standard Bratteli. So it's compact. And so we get local compactness. And such diagrams they appeared in the paper of Bratteli-Vershik of 2006, where they showed that every aperiodic Borel automorphism of the uncountable standard Borel space can be represented on this Vershik map in second. So this is important. So we can and I have a defined Vershik map, but it will be in a month. It's usually the same as for diagrams. This one's in 6, and so every Borel using Borel automorphism. Borel space is Borel as a unit. And it will be in a second defined to a Vershik map. Acting one defined space. And generalized. And also, all uncountable standard Borel spaces are Borel isomorphic in a similar way as all Cantor spaces are polymorphic. So it doesn't matter which exactly representation we use, so we can always represent our Borel systems on these generalized Bratteli diagrams. And actually, here we also prove that this Vershik map can be chosen in the real polymorphism. That this diagram has no can be ordered so that it has no minimum and maximum paths. It's also different from the standard case. So let us recall that what is an order Bratteli diagram. So in order to introduce dynamics, we have to put a partial order on the set of all edges. So if we have two edges, E maybe such that they have the same range, then these edges are comparable. So the two edges are comparable if not they want in the same vertex. So we have our Bratteli diagram, and for every vertex except for our level, we have many incoming edges, and we put a linear order on the set of these edges. And this is a partial order on the set of all edges. Now we can follow it the lexicographic, maybe it's also called inverse lexicographic order on the set of all parts, finite parts that end in the given vertex field. So if we have two finite parts, like this, and like this, such that they end at the same vertex. This means that we can compare EN and FN. So if they are different, if EN is, for example, bigger than FN, then at once we say that E is bigger than F. If they are the same, that means that EN minus 1 and FN minus 1 have the same range, so we can compare them. And so on. So we say that E is bigger than F, this finite parts. Even on the leaf, there exists J, broken zero, like this. For the trend, let's say, such that E prime is equal to F prime for every I from J to N, and each J is bigger than Fj. So that. And now we can introduce finite parts. They can be both finite and infinite. The maximum minimal parts, they can be both finite and infinite. So let me see. So if we have, for instance, for infinite parts, if it's called maximal, we can only if each edge is maximal among all edges comparable. And the same for minimum. And the same also for finite parts. So let's denote by X capital max and X capital min the sets of all infinite maximal and correspondingly minimum parts which start at the zero. So that's maximum corresponding minimum parts. These sets are always closed, but since we have non-compact space, they can be empty. And now we can define a Vershik map. So first we define what of the set of non-maximal maps onto the set of non-linear maps. So if we have some non-maximal infinite path, there exists some first index for which the edge is not maximal. So let's denote by n in zero all natural numbers and zero. So the edge xi is not maximal. So we have zero, so x is not 1 and 3. This is our first non-maximal edge. So it has a successor. So we know by maybe escape bar already escape prime successor xk, and then we form the image of this chart as following. So maybe that also denoted finally. So instead of this edge, we take its successor. And remember that successor has the same endpoint, right? The same range. So then the tail, we don't change it. It remains unchanged. And here we have changed this edge, and now we join the source of x k prime with the upper level with 0 by minimal path. And there is unique such minimal path for every vertex on every level. So we just see in unique way we can choose always minimal paths. So here
Like for adding motion.
exactly, yes, it's exactly, yeah, for generalization of the added machines. So maybe the best one we can is this example of standard diagrams. If we have a variable odometer, we put order on the edges, and for instance, let's look at this minimal edge of all zeros. So this is first one, if you want to see how vertical map acts on this. Yeah, so we look at the first non-maximal edge, and we change it to the successor, and then we don't change the tail. So if we for this part of all zeros, this 1, 0, 0, so on. Then if you want to again use a Vershik map, this is maximal edge, this is first non-maximal. So it goes with successor, tail remains unchanged, and here we go along the minimum path. So the next iteration it will be 0, 1, 0, and this x like edge plus 1. Yes, and now if we can prolong, so it's always a homing vertex between these two spaces. And if it can be prolonged in the whole speed, so here we don't usually instead of saying we ask that it's a homeomorphism, here we just ask that it is a Borel bijection. Then we say that we have a Borel generalized Bratteli-Vershik system. So for standard Borel spaces, if we have a bijective Borel map, then inverse is also Borel, and we have Borel homomorphism and Borel dynamical system.
Is it continuous?
So not necessarily, no, it depends. So we actually next maybe step we will consider these questions when it's continuous. Okay, so if I forgot something, then we can come back. But this was the introduction.
This was making for not maximal. Maximal goes to minimum.
Yes, exactly. So now we have to expand it so that maximal parts should go to minimum.
Starting from the same vertex.
No, just some.
Just any.
Yes, so that the prolongation is Borel, this Borel bijection. So the cardinality of this set should be the same. And actually, if they are like countably many of them, we can prolong anyway. This which is a Borel.
So on the 0 level, there is multiple.
Yes. So even in the case of standard diagrams, here there are many papers which study. So for standard diagrams, if there is unique minimum, unique maximum path, then Vershik map is always a homomorphism. Because from compactness argument, it follows that just continuous. Because if it was not continuous, there would be like another minimum path, infinite. And if there are many minimum and maximal paths, there is like a sequence of papers by Sergei Zungli, Rivia Sadi, Young Polsky, and others when people study like which orders give us and Vershik map which can be prolonged to homomorphism.
Have you assumed that from every vertex there is only a finite number of edges?
Yeah, no.
No.
Yes, it can be as
Now in each place you have plenty of choices to choose. Maybe you cannot choose minimal because there is a sequence of edges starting from the vertex. So which one would be?
But there is finitely many edges coming to a vertex.
Coming to, but then we start again, and then we replace from.
Yes, we are going backwards, so for every area vertex, we can find
There is
unique
finite
minimal.
Yes, depends.
So I switch it direct because here these three also grow up or down.
Yes, so here.
Okay, so here you have finite number growing from
Yes,
this.
yes.
Okay. Okay, I just reversed it in my mind.
Yes, sure. So let's make, we can consider the diagrams which are considered for every vertex. There are both finitely many incoming and finitely many outcoming.
Sorry, question
Yeah.
previous topic, is it possible to have uncountably many minimal or maximal?
Yes, it's possible even for seven. So we can have something.
Well, uncountable. Haven't we assumed it countable number of edges?
But maximal, minimal, number, maximal, minimal, first infinite paths.
So
And can be uncountable.
we can ignore something like, yes, let me just think for a second. We have to go on that. Zero, one, so here let's take left to right order. 0, 1, 0, 1. So here all these paths are minimal. And they form a tree of minimal paths. So this complete this whole concept it consists of the minimal paths. So there are counted many of them, and even the set of minimal paths has like one empty there. And here this one consists of maximum paths. So this is like in our paper with so much which we consider different prolongations of the Vershik map and whether they're all homeomorphic, whether the quantity or not.
What was that?
It's generalization of a many version. Like you can have many vertices on the chart, but it's actually has X like.
Oh, okay. This was this matrix it was. Fine. It's meant for
Yes.
whatever.
Yes.
Ah, yes, it was different version.
Okay. So even for standard diagrams, X max and X min can be accounted. And let's consider generalized Bratteli diagrams of one this size. So it is like an intermediate step between standard diagrams and like was the case of generalized diagrams. So here we ask and to each level we associate natural numbers and n. So this is our V0, V1. So for instance, fix a vertical level V1, and it has finitely many incoming edges. But what we ask is that their sources lie in some boundary interval, which depends on the level. So this is V minus T0, V plus T0. So for every, we can suppose that this level n plus 1, and this is level n. So for every n, and for every Vn plus 1, the sources of the edges which n in V, and here also let's assume that V and U will make vertices by integers. So that also this V can be looked at as a number, each vertex is eliminated by integers, and here this number is V minus T0 and V plus T0. And this happens for every vertex. So this belongs to the interval V minus T0, V plus T0, and also the number of these incoming edges is also uniformly bounded by some LM, which depends on the level. So here we have this T and A. So the number of incoming edges is randomly bounded. And this macros are all on the side. If for every n we have stationary sequences of Cn and N, we say it's uniform now. Then the Borel, and let's consider as an example.
So are multiple edges allowed?
Yes. Yes, thank you. I didn't say that. Yes, we can have multiple edges. So if we consider just 0, 1 incidence matrices, and for instance, stationary diagram, so stationary means that all incidence matrices are the same, that it means that in all levels the edges are drawn in the same way. Then our path space is the same as for countable Markov sheets, but we have different dynamics. We have sheet and we have Vershik. But the path space is the same. Example. So maybe here. So our vertices are related by inverters. And for instance, we can consider the following stationary diagram. And then it goes in the same way. So so remember that in each level, we draw edges according to the rule which is given by incidence matrices. So here for every edge.
Remember, vertices at each level is the same.
Yes, exactly. Let's
In
also
particular.
yes. That's also a thing. So here our matrix is as follows. So it's by infinite matrix. So for instance, let this be our 0 coordinate. So from 0 to 0 we have 2 edges. From 0 to -1 we have 1 edge. From 0 to 1 we have 1 edge. And so our diagonal will consist of 2's. And then above and below the diagonal we will have 1's. And otherwise we will have 0's. So this will be, this is like coordinate, 0 coordinate. So this will be our matrix. This will be incidence matrix. So it's stationary diagram, so it's the same for levels. And so here our T is equal to 1, right? So here, if we start at the vertex, we can only go one step to the left and one to the right, and we don't connect vertices which are further away. And L is equal to 4, right? So there are only 4 independent. Okay, so these are not the diagrams of the boundaries on the side. And also, here, for simplicity, we adopt the following convention that the number of elements between B minus Tn and B and B plus Tn and B is non-zero. So there is always this like rightmost edge and leftmost edge. So sometimes we will be able to draw this condition, but sometimes it is important for some areas. So we will also have this. And now let us look at the structure of this generalized Bratteli diagram. So let's start with some vertex which belong to Bn plus to some n level plus 1. So we know that all vertices which have edges which can reach to this vertex V, they lie in the following. They have the following range, right? Like the sources can come from this input. Now we can go again one level down, and now the sources can come from the following interval, and so on until we reach this 0 level. So we have something that we can call an upper cone. So if we have a vertex for every non-negative natural number for every V, we can consider the sources of all paths that end in V. So the sources that belong to 0 of all paths that end in V belong to the interval So it's V minus sum of Tn's from 0 to n. And V1. So remember that it's V just an integer. Okay. So try to find orders by actually can show this. And also this structure gives us in the same way the downward cone. So we have this cone. And now we can also do a downward. So this will be the rightmost edge for the vertex V minus Tn, so Tn plus 1. And here it will be V plus Tn plus 1, because here the level between Vn plus 1 and Tn plus 2, we have this parameter Tn plus 1. So here we again all have the same way the downward cone. So here the rightmost vertex we can achieve, we can reach for is V plus Tn plus 2 plus Tn, V plus Tn plus 1 plus Tn plus 1. We have the same with minus. So from this, it follows that we have local compactness. So every cylinder set is represented as a standard Bratteli diagram where we have a bounded number of vertices on each level. So the path space is locally compact. And this diagram seems to be among the simplest generalized Bratteli diagrams. And we decided to look at the simplest order, which is left to right. And it turns out that the Vershik map is not always continuous. So sometimes if we have left to right order, it's never possible to prolong the Vershik map to a continuous map. And there is a condition, so there's a error. So suppose we have a generalized Bratteli diagram of bounded size. It has parameters T and S, right? And suppose that wherever we end, there exists A such that T. So with a characterization of this sequence, Tn plus k is less than the sum from n plus k minus 1 Tn. Then however, we continue. So actually, I should also say that for such diagrams, the account of remaining medium are included away from left to right. I mean, the account of remaining minimal paths and count of the very maximal paths. But then we finish this sentence, then any Vershik map on the path space of this diagram is non-continuous. However, we prolong it. And moreover, every maximal path is a point of discontinuity. Every infinite path is a point of discontinuity.
Is this network in the right direction? Tn plus k less than, which means this means it's so we don't not grow much.
Yes. I mean, yes. So
one would expect that it is rather continuous, not just.
it's not. So for instance, uniformly bounded Bratteli diagrams have this, like we drew before, and has this property, right? So here they are all just the same. And so we have this. So here there's no continuous version. If we are integrated from left to right.
Why it is not continuous?
And let me do. So first here it's indeed important. Maybe maybe we can relax it, but for now let's assume this. So let's see if we have any vertex V on level n plus 1, then there is this unique rightmost minimal path. We have order from left to right and leftmost. And if we take another vertex, it will this maximal edges will go parallel, right? because we know that there is the same, this Tn depends only on the level, and we know that there is such edge. So all these maximal and minimal paths will go, like we can say, parallel to each other, into each other. So they are countably variable, and so each vertex passes exactly one minimal path and one maximal path. So that's what we have. And here we will show that for every infinite maximal path, as denoted by x small max, and this is the set of infinite maximal paths, for every epsilon, we can find two non-maximal paths such that in the epsilon neighborhood of x max, such that the images on the Vershik map will have a different score for any Vershik map. So we have like our left to right order, and we promote the Vershik map in arbitrary ways so that its map is a Borel widget. And so we have our phi b, and then we show that phi b, the distance between phi b of x prime and phi b of x prime is equal to 1. So we don't have continuity. And let's see. So our maximal paths go like that. So we can find here level n. So here we have level 0, we have x0, like corresponding to the maximal path. And here we have x1, so here xn minus 1. So this is a piece of our maximal path up to level n. So we have n epsilons. So remember we have a metric. So pick n such that 1/2 to the power n minus 1 is less than epsilon. Now we choose x prime. So x prime follows the maximal path up to level n. Then it goes along the minimal path, and then in arbitrary way. So this will be our x prime 0, x prime 1. So we have x prime I is equal to this maximal I for every I from 0 to n minus 0, and x prime n is a minimum edge. Now we have for every n this condition. There exists k. So go down k plus 1 edges along this maximum path, and then x double prime here at level n plus k, I believe, for n plus k plus 1, n plus k plus 1. Here we go along the minimum path, and then continue in arbitrary way. And here, basically, the idea is that since we have this condition, when we look at how Vershik map ends here, this is first non-maximal edge, so it will be mapped to its successor, and we go along minimal path. This maps to its successor, and we go at minimal path. This minimal paths will be different. So we don't have continuity. And actually, if this was big enough, so we can have continuity only if we fit in this neighborhood of the same model. So should I write like more careful, or it's okay?
It's okay.
Yeah, because we have in some origin data, we will a little bit brush it out, but this proof is on the outside, like very in details, but basically it follows from here. We know exactly the structure of the code. So even if we pick here the last possible edge, and here even if next one is in this vertex, still they go differently. But there is an example when Vershik map is continuous. So there's classes examples. So we have again generalized Bratteli diagram on bounded sides. And we ask that every vertex has only two common edges. And we say that there exists n. We take like at the beginning of the negation, there exists n cycle for every t, t inverse n plus p. And here we ask equality. And let me give you an example in a second. Then the vertex map can be prolonged to 100 modes. So there exists only one vertex map. And let's, for example, consider a Bratteli diagram for which this condition already holds for n equal to 0. So starting from 0 level. So this is exactly the following diagram. So here n is equal to 2 for every n, and we have T0 equal to 1, T1 equal to 1, T2 equal to 1 plus 1 equal to 2, T3 will equal to 2 squared, Tn will be 2 to the power n minus 1. So we will have exactly that condition starting from 0 here. So let's see what it means. T0 is equal to 1. So we go like this, and then only two incoming elements. So we have ones. Then next level again the same. T1 is equal to 1. Then next level. So for instance, this is our 0, 0. Our next t is equal to 2. So we go like that. Yeah. I mean, it's a little bit maybe not very nice. This would be a lecture, but so we have. Then we go here like that, like that. Then in the next level, we have the edges are like that. The following way. And so let us we claim that it is. So it can be actually any level, but for simplicity it would be 0. So here, if we have this maximal path into this maximal path into this minimum, we don't have contribute. Because we can look at the neighborhoods. So this is non-unique, like non-maximal paths that coincides here and then goes differently because we have only two common edges. So to look at its image, we go here and then this minimum path. And they are so well aligned that when we go down here, again, we go to the neighborhood of the same minimum. So they have really to be aligned like that to give us continuity. Yeah, so basically this is that example that we have. And now let me move on a little bit to pair equivalence relation and to stationary diagrams, and then we come back to bounded side diagrams. So now the properties of pair equivalence relation. So let's recall that if we have independent parts, their tail invariant. If and only if there exists such level, such that starting from it, that like the tails coincide. So all edges. So so this is how like and then we have the same tail. So this is called tail equivalent relation. And suppose we have as there's a theorem, let B be as a stationary generalized Bratteli. So the incidence matrix is the same for all levels. And let L be the incidence matrix. And here we assume that L is irreducible and aperiodic. And we use the as our textbook. We use the book by Kitchens on symbolic dynamics, where he has chapter 7 about these infinite matrices. So here we use the book by Kitchens, symbolic dynamics. So here he uses this knowledge to Markov shifts, but we can still use knowledge about the matrices, but we have different dynamics. So it's symbolic dynamic. So irreducible is the same as for finite matrices, that for every pair ING, there is a power of matrix such that element IJ is not zero. And aperiodic, it means that we can take like all possible n such that fn is positive, and then we have various common divisor of such n. So so with this matrix F, we can associate a graph, right? So a graph on this integer. So again, here we assume that our vertices are generated by integers, and so for every two integers I and j, we can consider integers as vertices or group, and there is a path from I to j if f I and j is positive. So, aperiodic, it means that we look at all possible paths from I to I and at their lengths, and this greatest common divisor of this length is equal to 1. So this is aperiodic, and this is our assumptions on the incidence matrix. Then their equivalence relation is topological addressed. So what we prove is that in our diagrams, there exist paths, there are the so-called like vertical paths, such that its tail equivalence class visits every slither cell. So the tail equivalence class of X, when we take a closure, it will be in the whole path space. And let's see what it follows. So let us start with arbitrary vertex type. First, our matrix is irreducible. So there exists a risk such that the case power of n. Right, so for irreducibility, we can take j equal to I. So there is a finite path from I to I. So on the diagram, we have our 0 level, this is finite. Then after these steps on level VT, we know we again can go to I. And again, at the 2k and so on, some x times k, where s is a natural number, we have this vertical path. Now consider arbitrary cylinder set generated by this finite path. So suppose it ends in some j. So maybe here is our level n, there is vertex j, and there is some cylinder set. So what we want to show that it is possible to reach this cylinder set, right? This finite path. So here we go some j. So first, again, we use it to get this, we use irreducibility. So we know that, so we have fixed I and j. We know there exists like some natural C such that f to the power t I j is positive. So we can come from I to j in these steps. And now we have to join j with j. And here we use lemma from Kitchens, which is true for irreducible aperiodic matrices. So it says that for every j, there exists some integer m, natural number, which depends on j. such that for all A greater or equal than n, S power of JJ is positive. So basically here we can go long enough, this length is M, and afterwards, for every level, we will be able to reach J. So that's enough for our proof. So here we take S long enough, such that when we subtract T, still this path is long enough so it exists. So basically, and that shows us that there is a tail path, tail equivalent to X, which belongs to this smaller set. So it's the logical but it has a separate minimal. And actually, generalized Bratteli diagrams of bounded size, they give us example of, for instance, we can take them stationary diagrams which satisfy conditions of theorem, but for which our equivalence relation does not mean. So it's topologically transitive, but not every path has a dense orbit under equivalence relation. And actually, since we have these infinite diagrams, there appears like some slanting infinite paths. Like this, so vertical path will have dense orbits, but this slanting path will not. And let us see. So let's come back to so now it will be true also for non-stationary diagrams. So let B be the generalized Bratteli diagram of bounded size. So we have these parameters Cn and n for every level, and fix any vertex W on 0 level. So again, I enumerate vertices by measures. And now we have here some, so it's like 0 level. So then we have the rightmost vertex that we can reach. It has a number by a W plus 0. And then from this, we again took the rightmost possible, and so on. And consider all infinite paths, which only pass through the edges that lie in this, to the right of this infinite path. We call it this slanted set corresponding to W with plus. We can take the same with minus. And then there's also a lemma or a theorem that these sets for every W, they are closed, nowhere dense, are invariant sets. So for closed, nowhere dense, are invariant. So we see that we don't have linearity because of this paths. So here, to be on the safe side, let's assume the reducibility of the diagram. So remember, so it follows from this structure, I think, that the diagrams for bounded size, from the fact that they have these upper cones and lower cones. So what is this tail bend? Because if we take, for instance, like even this path, any path from here, so we fix like the tail, and then the sources only lie inside of this cone. So we can, since we look here like right one possible path, we cannot get out of this. And this is true like for any path that we take. Remember, these paths go parallelly. So we so this is our invariant. Then it's easy to see that it's closed. It's basically a subdiagram. So we can take this union of cylinder sets on 0 level. It's a closed set. Then on level 1, we take all cylinder sets on 0 of length 1, which only belong to this set. And then so on, we have the nested sequence of closed sets, and their intersection is our paths. And it is nowhere dense because it doesn't contain any cylinder set. Because once we have any cylinder set, it has a cone like this. So we will always get out of here. So if, for instance, we have a stationary diagram of bounded size, and we assume irreducibility, that means that for every vertex here, and we pick up vertex outside of this vertex space, there is a path. So for every cylinder set, we have a cylinder subset which goes out of our set. So we have result like this.
So the conclusion is that for such diagrams, the R is not minimal, right?
Exactly, yes. So I think now we can go to measures. Yeah.
We confused how R is related to Vershik. Is it orbit conservation of the vertices?
So if we have, for instance, no minimal, no maximal paths, then it's exactly this orbit of Vershik map, or exactly the same as orbits of our equivalence relation. If there are, then it's the same as for standard diagrams. We have problems for because maximal paths can perhaps not their equivalent minimal paths. So we can do orbits. But for instance, if we want to look at invariant measures with respect to Vershik map and with respect to this equivalence relation, if we have like countably maybe, for instance, minimal maximal paths, and we look like at non-harmonic measures, then the measures will be the same because it's
So about
so basically it's the same problem as for the division by numbers. So indeed, let's look at the numbers. So the measure, so we consider Borel, non-atomic, positive measures, and speed. And the measure is R invariant. If for every cylinder size corresponding to some finite class E and M. If the range of E is the same as the range of M, then the measures of corresponding cylinder size are the same as for standard Bratteli diagrams. So if we have, so these finite paths, they have the same lengths and they end in the same versions, they generate cylinders, and the measure should be the same. Then we have to.
Could you remind me what is this capital R?
What is what?
Capital R. This.
It's the equivalence relation.
Hmm?
It's the equivalence relation.
What was this equivalent relation?
And it seems that the paths have the same tail. So they're equivalent if we can find a level starting from which we have the same tail.
Okay.
So now let us notice, we have our and we have corresponding incidence matrices, right? Which tell us how the edges are drawn. So here we have 0 and 1, and we have some edges. So the measure of the cylinder set depends only on its endpoint, right? Because the measure is available. So let's know why it's also the same for now as for standard diagrams. So let's, for instance, PWM. So suppose we have a invariant measure. An invariant measure such that it takes finite values on all cylinder sets. So we assume that mu takes finite values. In particular, it is sigma finite. And you know, by PWM, the measure of a cylinder set, which ends in the vertex W on level M. So all such measures are the same because it's the invariant measure. So measure of a cylinder, any cylinder which ends in the so we have this cylinder, then it is partitioned into sub-cylinders. Can be finitely made, can be determined. So, and the number of edges between V and W is given by the edge of our matrix, of incidence matrix. So we can say that P W is the sum for all B in B plus 1 of the measures of cylinder sets on level n plus 1 times this number of them. So the W n. So here we see that if we take transpose matrix to the incidence matrix denominated by A, then we see that PW is equal, so let's translate and transpose. So here let's denote by Pn the number of measures of the cylinders. So we fix some length and consider all the vertices and measure of cylinders. So vector of measures of cylinder sets which enter this radius. So the vector of this, so P is the vector of this ends. And so if we have some invariant measure, then just from common law of consistency, it follows that we must have this equality between these vectors of measures, right? Just because we have a measure, and vice versa. Once we have such sequence of non-negative vectors, they completely give us the measure. We can just use the category construction, build a Borel measure, and it will be there. So once we have the sequence, we have the invariant measure. Now, maybe the first thing, not all generalized Bratteli diagrams have invariant measure which takes finite values on all cylinder sets. So such measures don't always exist. And here is a very simple example. Of a stationary Bratteli diagram which is not, I mean, it's reducible, it is not irreducible. So suppose we have now we enumerate for simplicity by natural numbers. For this example, our vertices. So suppose we have here stationary diagram such that here we have vertical odometers and the edges grow. So here we have 2 edges, here 2 edges, 3 edges, 4 edges, and so on. And we go to infinity. So such diagram does not have an invariant measure which takes finite values on cylinder sets. And so we have no invariant measure which takes finite values on cylinder sets. So let's prove it by contradiction. So suppose it takes finite value, like example of generality, some positive finite value on this percent. So we can normalize, for instance, this measure such that the measure of this cylinder set is 1. Then our measure is stable beta. So the measure of this cylinder set will be the same, right? 1, 2, 1, 2. Then we go down, we again divide by 2. So the measure of the set is 1, 4. So it's like every measure, right? And now let's look at this cylinder set. It contains this sub-cylinder. We have 10 invariant measures, so it should be 1. Then it contains 3 sub-cylinders of measure 1/4. So let's ignore, for instance, by U, this cylinder set. So measure of U is bigger than 1/2, 1/2 plus 3 times 1/2 squared. Then we go one level down, we have here 1/8. And here we have 3 squared possibilities, right? Some finite number. Plus 3 squared times 1/2 plus so on, and this is infinite. Right, because here it's like geometric, some geometric progression with where we multiply by 3/2 each next element. So such a diagram does not possess the invariant measure finite on cylinder sets. And now, what helps us to build measures, for instance, on stationary Bratteli diagrams, is the Frobenius theory for infinite matrices. The same as for standard diagrams, we have Caron-Frobenius theory for finite matrices. Here we have for irreducible periodic matrices, and it's developed in this theory of countable Markov sheets. Once we have so let me start with some irreducible periodic non-negative real numbers. And then we can consider lambda is the limit and then goes to infinity of the nth root of a to the power n. AI for some, suppose it's liberated by integers, and I is some integer. So then there exists such limit, and it is the same as supremum over more n. And since it's irreducible, it does not depend on I. And it can be finite or infinite. So now there are matrices with infinite Caron element. And the matrix is called recurrent. Like such under such assumptions, if the sum of so a to the power 0 is identity matrix, and we construct such series. So we assume here that lambda is finite. And then if this is infinite, then we see A is recurrent. So this notion is used usually in Markov chains for stochastic matrices. So for lambda is 1, and A is a stochastic matrix. And it means that for every I, the expected number of returns to I is infinite. So it's called recurrent, and it's called random. If this is finite, if this sum is finite. So here we have irreducible periodic non-negative matrix. We define a periodic value like this. If we assume that it is finite, then matrix is recurrent. If we have this condition, and if we have this one. So it means that expected number of returns to I is finite, and then it goes on. So it's not recurrent. And for recurrent matrices, we have Caron-Frobenius eigenvectors that will give us an advanced invariant measure. But this eigenvector, I didn't find any conditions, like explicitly written conditions on the matrix, which tell us whether eigenvector will have summable coordinates or not summable. So the measure that corresponds to this vector is finite or sigma-finite. So it will be finite on Smith's set. So it's taken from the book of teachings, and this actually was done by Beer-Jones. It's like Beer-Jones classification of these matrices, but very good. Like we used to the source by the 10th book. So if A is recurrent, and we have all those conditions, irreducible, periodic, non-negative, real, Caron eigenvalue is finite, then there exists uniquely defined up to multiplication by a constant, positive vectors. Side there with right side equal to lambda side, and A from A is equal to lambda A. So we will use this method. Once we have it, we can define the measure. So we can which ends in some work at the on level. We can define the measure of this set as W coordinate of this eigenvector over lambda to the power n in the same way as the standard methods. And that's since we have this equation, we have this consistent form. So our measure will be determined.
Do you still assume what is this condition boundedness?
No.
No?
Yes, so just for instance, there is in fiction book also, and it is Jakob showed us the example, it's master physics. So we can have, thank you very much, but it's not necessarily bounded size. So we can have so-called, and I'm going to say that this stationary value numbers correspond to substitution level systems. In particular, bounded size, like the paper by that they show that those stationary bounded size Bratteli diagrams and the Vershik map there is conjugated to substitution level system on account of their infinite component. So they are also interested in dynamical and this is so-called residual shape, like the space, like this diagram corresponds. I think to the residual shape. And so here you see, so this it's matrix transposed to inverse matrix. So here we have from the so let's enumerate vertices by natural numbers. So here we look, it's transposed to incidence, so we look from upper level to lower level. So from the first vertex, we have one edge to every other vertex. Then from the second, we have like one here, so it's a level of the number. And then we have here equal column sum. Sorry, here's one. So the sum in every column is equal to 2. So we can take one that equal to 2. And then we can check, it's easy to check that the corresponding right eigenvector will be 1 over 2, 1 over 4, and so on. So it will be 2, and it's straightforward to check. So this will give us sigma finite, finite examples that will give us a finite invariant measure. So here we don't need anything. So as soon as we basically have this sequence of vectors, like this inverse limit, we have a measure. If we have an eigenvector, positive eigenvector with zero negative value, then we have already a measure. And we don't need bounded size, we don't need stationarity. I mean, the eigenvector is stationarity, but for sequence of vectors, yeah, it's general.
Just do you have a left eigenvector for this?
Yes, it's all ones. Yes. So actually this matrix is so-called positive recurrent, and for such matrices we can show that the Bratteli diagram has a unique Gaussian invariant matter, which is probability, and which gives positive values for every single. So basically the class of recurrent matrices for which we have such vectors, it's subdivided into the class of positive recurrent and non-recurrent. So we know that we return to any point. Like we start with I, we will have to return to I, but we look at the expected return time. It can be finite or infinite. So the matrix is positive recurrent. One of equivalent conditions. It means that so psi is our right eigenvector, it's a column. Eta is a left eigenvector, it's a row. So if we have this condition, we have positive recurrent. It means the expected return time is finite. And if it's infinite, it means that it's not recurrent. And there is a theorem. So if we have a station in the generalized diagram with incidence matrix yes, and A transpose to incidence matrix, such that our A is like we have all these properties, it's irreducible, periodic, positive recurrent. Then there is a unique harmonic invariant probability measure, which gives positive values for every single set. And this is exactly defined in the following way by the vector. So where E is a finite part, which ends in 1. And it follows from the statements about positive recovered matrices. So it's another statement from the book by Hitchens. So once we have a positive recurrent matrix, so inside this definition we include that it's incidence irreducible, periodic, all these things with finite, periodic, and vector. And we can normalize these vectors such that f times psi is equal to 1. Then the limit as n goes to infinity of a to the power n like I over rather with the I maybe you double let's say like this. So this is a to the power n element VW is equal to, and here we multiply plus vice versa. So we get a matrix. So we multiply this vertical column vector by row vector, and we know basically how our elements grow. And using this theorem, we can prove that if we have any other ergodic invariant measure positive consider sets, we use, it's also like often used in the papers, this tool for how ergodic theorem looks for Bratteli diagrams. So we have, for instance, some cylinder set, which ends in W on level n, and then we take any other vertex V, which is somewhere far away below, and we see, actually here, I forgot to say that we also have, of course, a Vershik map here. But maybe because we want, it's ergodic with respect, we use the both theorem for Vershik map. We see how many times we visit our cylinder set, and mark this in this when it goes from this tower. So there is a formula that the measure of this cylinder set is the limit when n this level goes to infinity of the number of paths between W and V. Remember, we do not just read like this over the height here, over maybe but we don't know by height again first. Okay. So we take, we see the number of all finite paths that end in V. It's our denominator, and our numerator is this path. So when we hit, when we visit this cylinder set. So the number of visits of cylinder set over the height of the tower. So H V is the number of finite paths that start at V0 and finish in V. So let's finish in V. And basically, when we assume that there is any other ergodic invariant measure, and then we can express this in terms of our matrix. So we know that this is so maybe let me know, right? So we have this vertex W in level n, and our n is fixed, and then we have our level n capital, we have V. So the number of points here is a to the power n minus 1. Okay, so a goes from up to down, so we have W. Right, is the number of the starting part. Then when we want to see the whole height here, height for the vertex V, it opens the sum or all of u in this zero of a to the power n u. And then we have to divide this by this, and n goes to infinity. And then we use that element, maybe it still stays there from each of the book. We have positive recurrent matrix, so we will use it. So let's divide this by lambda to the power n minus n. Divide this by lambda to the power n, like this thing, so it goes to the numerator. And so that we have a unity, we can also multiply by lambda. And now we know that this thing from this area. So here again we start with this eigenvectors. So let's first normalize this one, which gives us measure, such that the sum of coordinates is 1, and then normalize this one, such we have this equality. And so here in the image we have so it goes sine w times eta v over the sum of psi u times eta v times lambda to the power n, and then this will normalize such that this sum is equal to 1. So we get exactly the formula for the measure. So any other algebraic probability invariant measure positive considered sense will have the same measures on this sense. And one can do similar thing for sigma finite measures using a whole ratio algebraic theorem, which tells us that the ratio it will follow in our case the ratio between the measures between two cylinder sets is the limit, like similar thing. So let this ends in V1, this ends in V2. So we find a W somewhere below, which expects that after both to V1 and V2, and people consider number of parts between V1 and W, and number of parts between V2 and W, and this measures, and this n goes to infinity in the second. So in similar way, we can show, but I mean, there is also a condition that the system has to be conservative, which we don't really know how we're going to write the diagram yet. What are the conditions? But to use this theorem, we will need that Vershik map is conservative, and then we can use this and again show that there is after multiplication by a constant unique sigma finite measure, which is positive in all cylinder sets. Finite positive. Yeah, so in case when this vector psi is non-summable, so we have this eigenvector, it can be summable or a sum of coordinates can be infinite. But after we multiply by eta, still we can get this. So we have finite or sigma finite measure, and also what are the results we have? So we can pass to. We can pass to Markov measures. So when we want to determine whether matrix is recurrent or transient, there is a way. If we have an eigenvector, we can create a stochastic matrix with the help of this eigenvector. And actually, Tiana share proof for us that if this corresponding stochastic matrix is recurrent, then the infinite is recurrent, and so on. That we can use knowledge from Markov theorems. And actually also there is a paper by Cantor and Joseph Bobock. It's actually a part of series of papers. There are papers by Michal Mitrovic, Samuel Roth, Cantor, Joseph Bobock, where they study countable continuous countable piecewise monotonic maps of the interval. And they appear also with infinite matrices. And for instance, actually we have lots of examples, I don't present that here, for which we can say when this eigenvector has summable coordinates or not summable coordinates. So we have some class of examples, like this banded matrices for bounded size diagrams. And also some class, also we have some sufficient conditions for non-bounded size diagrams when again we have summable eigenvectors. So for instance, like for this renewal sheet, when we have a whole row consisting of ones, and we find an eigenvector, then of course it will be an sum. Also, if we have only, if for instance, we have a row where ones are open, and next row where ones are open positions, then again we can deduce the eigenvector sum. So we have some like a pretty generalized version of this condition. So a global example. So since we have the following matrix, it's not following unit. So there is a huge question about what if it's not positive recurrent matrix, if it's reaction, or if it's not recurrent. So here we can come to the course. So here it has 0 mean dynamical is below this above, and here actually there are many eigenvalues and many eigenvectors. So we gave example of 2 lambdas. So first lambda is A1 B. Second lambda is that here respectively used it 2 times square root of AB, and we give formulas for eigenvector. They both generate invariant measures. If we like look here, for instance, for this lambda, we can produce rank walk on the corresponding graph with those to the left with this probability and to the right with this probability. So if A is equal to B, then these 2 numbers are the same, and we have like now recurrent matrix. But when A and B are different, here we have tangent matrix. We don't refer to the point from where we started. And here, actually, I think it follows from their papers, we can have independent lambdas. For any lambda bigger than this, there is a corresponding eigenvector, which gives us an eigenmeasurement. So we gave it like for this for lambdas, but there are like uncounted dependent. So it's completely different situation than in standard diagrams. And I think maybe let's see. Yeah, so the paper is on the archive, but we will soon upload it in the second version, where we'll have some more examples and like fix some misprint's. But I think that's it. Thank you very much for the.
So in this example, you can have uncountably many recorded invariant
The
matrices.
things are going almost from this very general classification that is like French matrix. So there is this series of papers where they consider this continuous count of the piecewise monotonic maps, and they show when it's like look at the entropy and when they contribute to the constant slope maps. And actually, yes, there is. If we understand correctly, yeah, there is a result that for all lambda bigger or equal than this spectral radius, so they computed it in the paper, Cantor was involved. There will be a corresponding positive eigenvector, and then once we have eigenvector, we will have a measure. But we haven't yet like looked more carefully into this types of examples.
Another question? Also, you want to continue? Okay. Other questions, comments? I have one more question. So, do you know examples when the set of ergodic measures is not closed in mixed topology?
There's a paper by Olena and Karpel, some countable work of shapes. So we have to look carefully about this topology. There is a topology of convergence on standard sets. So we haven't yet looked very look there, but we are in the process. But it's really complicated because here we don't have this compactness. So yeah, it's like yeah, we get like more complicated situation.
Any other question?
Yeah, so I think that all the technical examples we have for now.
Any questions from online participants? No? Okay, let's thank you again. the online participants, and see you next time.
Hello, everybody.
Hello.